Hi everybody, this is Naz Saqib from Texas Tech University. Today the topic on which I'm going to talk about is an overview on trust region method with special focus on Levenberg Marquardt algorithm. To start with, let's discuss a few points on the general properties of optimization algorithms. All optimization algorithms require the user to supply a starting point, denoted by x0. Beginning at x0, optimization algorithms generate a sequence of iterates x1, x2, x3, xk, xk plus 1. Process of iteration terminates when either no more progress can be made or seems the solution has been approximated with sufficient accuracy. Now, for moving from the current iterate xk to a new iterate xk plus 1, most of the continuous approximation algorithms follow one of these approaches, line search method or trust region method. Now, let's talk about a few basics of trust region methods. Trust region methods assume a model Nk that approximates the objective function in a finite region near xk. This region delta, where the model is a good approximation of f, is called the trust region. These methods choose the steplet delta to move towards the approximate minimum of the model in this region, and also update it at each iteration using heuristics. This figure represents a resemblance of behavior between an objective function with its quadratic model. It's pretty clear that near the minimum of the objective function, the behavior or trend of the function is pretty closely approximated by its model. Now, this figure is actually a comparison between the approaches that are taken by line search and trust region methods. If you look closely, you'd find that the line search methods, starting from an initial point, moves straight away towards the minimum of the model, whereas the trust region methods are moving in a somewhat different direction. But if you think about the values of the functions, you'd find that the trust region methods are not only minimizing the model, but also they are remaining near to the global minimum of the objective function, whereas line search methods are deviating from the global minimum. The model Mk that is usually approximated by the trust region methods are of quadratic form. These are obtained by a Taylor series expansion of f around xk. That means Mk equals function of xk plus gradient of function of xk dot p plus half of p transpose hp, where h is the Hessian or an approximation of the Hessian matrix. The subproblem to be solved to find the step length to take during the iteration is given by min norm of p less or equals delta, the step length, function of xk plus gradient of function of xk dot p plus half of p transpose hp. The iteration step is given by xk plus 1 equals xk plus pk. The heuristic to update the size of the trust region usually depends on the ratio of the expected change in f to the predicted change, which means rho k is given by difference between the function value at the current iterate minus the function value at the projected iterate divided by the model value at the new current iterate minus the model value at the new iterate. If there is a good agreement between the predicted and actual values, if rho k is closely equal to 1, then delta is increased. If the agreement is poor, then delta is decreased. But if the agreement is smaller than a threshold value, the step is totally rejected. The value of xk is retained, but delta is decreased accordingly. This is in fact a generic trust region algorithm one needs to follow while solving the optimization problems using this algorithm. Some examples of trust region algorithms may be Levenberg Marquardt, the most popular one, Golub and von Mack, dogleg, double dogleg, two-dimensional search method, and truncated conjugate gradient method. Now, the Levenberg Marquardt method was first put forward by Kenneth Levenberg in 1944 to provide solutions for problems called as nonlinear least squares minimization. The update function was a blend of the characteristics of the steepest descent and the Newton's method. It was improved later by Donald Marquardt in 1963, who incorporated the estimated local curvature information into the update function. The original algorithm was put into the trust region framework by Moore and Sorensen in 1983. These pretty popular algorithms are used in nonlinear least square programming (NLP) with unconstrained or unbounded constraint problems. Now, the function to be minimized is of the following special form: f of x equals half of summation of j equals 1 to m rj square of x. Rj's can be represented as a residual vector defined by Rx equals R1 of x, R2 of x, dot 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 Rm of x. F can be rewritten as f of x equals half of second norm or 2 norm of Rx squared. Trust region algorithm chooses the model function to be mk equals half of norm 2 norm of Rxk squared p transpose Jacobian of xk transpose Rxk plus half of p transpose Jacobian of x transpose Jacobian of xp. Now, the subproblem to be solved to find the step length to take during the iteration is given by min of norm of p less or equals delta half of r of 2 norm of r of xk squared plus p transpose Jacobian of xk transpose r of xk plus half of p transpose Jacobian of x transpose Jacobian of xp. The solution of the subproblem is given by the following theorem that was put forward by Moore and Sorensen. The vector p star is a global solution of the trust region problem if p star is feasible and there is a scalar lambda greater or equals 0 such that the following conditions are satisfied: h plus lambda I p star equals negative g, lambda delta minus norm of p equals 0. H plus lambda I is positive semi-definite. Now, let's look at few different cases. When the solution lies strictly near the trust region, when delta equals delta 1 in figure 4, we must have lambda equals 0 from condition 2 and p star becomes equal to negative h inverse g from condition 1, with h is a positive semi-definite from condition 3. But if delta equals delta 2 or delta equals delta 3 in figure 4, we get norm of p star equals delta and lambda greater than 0 from condition 2, with h is positive semi-definite from condition 3. For such cases, we define p lambda equals negative p plus lambda I inverse g, which is in fact a one-dimensional root-finding problem in the variable lambda. By defining phi of lambda equals 1 over lambda minus 1 over norm of p lambda, we apply the Newton's method and get the update function as lambda L plus 1 equals lambda L minus phi of lambda L divided by phi prime lambda L. This is the algorithm to which the subproblem needs to be applied. Now, let's talk about a numerical example. Let's consider the following function: yt, function of t and p, equals p1 exp negative t over p2 plus p3 into t exp negative t over p4. Now, let us denote true parameter values as p true, initial estimate values as p initial, resulting curve fitting parameter values as p fit, and standard errors of fitting parameters as sigma p. If we look at the table, we get that the sigma p over p fit values are pretty near to 0, so the curve fitting problem has converged quite successfully. If we look at the figures, we get that the function has a single minimum, and after 22 maybe function calls, the parameter values actually converges quite easily or successfully. Applications may be nonlinear least square solver, this method, optimizer for sum of squares of functions, and optimizers for general functions. And these are the references that I followed to prepare this talk. And the last one, the book, is pretty useful. You can follow this. So, happy programming!